Shooting thousands of pounds of metal and human cargo through the literal vacuum of space leaves absolute zero margin for error. To navigate that void safely, thousands of engineers in mission control relied on the Apollo guidance computer to execute the complex mathematics of the lunar landing in real time. Yet, the device sitting quietly on your desk right now possesses vastly more capability than that entire room of historical equipment. The Apollo computer operated with about 1/millionth the processing power of a flagship device like the iPhone 17 Pro Max. If you wanted to match your current smartphone's speed and memory using strictly 1960s hardware, you would need millions of Apollo-era computers processing data simultaneously. Visualizing that millionfold leap in computing capacity means picturing a physical machine the size of a modern city. Housing millions of early guidance computers together to match one iPhone would require a single, unbroken warehouse swallowing dozens of city blocks. Attempting to power up that sprawling grid of vintage processors would pull enough electricity to instantly crash the regional power grid. All that energy consumption generates catastrophic heat. Without an industrial cooling system the size of a lake, millions of 1960s components would melt themselves down into slag within minutes. Even if you kept the warehouse cool, you hit a strict physics bottleneck called data latency. Latency is the built-in delay of sending electrical signals across a physical distance. By the time an instruction travels across miles of copper wire from one side of your city-sized computer to the other, loading a basic web page would take hours. Physical space, thermal limits, and the laws of physics make scaling older technology outward a complete dead end. To bypass those physical limits, the engineers who followed the Apollo program stopped building outward and started building inward. The silicon architecture driving your smartphone solves the heat and distance problems by shrinking down the components to microscopic scales. This image shows the highly dense circuitry of a modern microchip, built using nanometer architecture. A nanometer is exactly 1/1000th of a meter, a scale that allows manufacturers to carve millions of computing pathways mere fractions of a millimeter apart. Because electrons only need to cross those fractions of a millimeter instead of traveling through miles of warehouse cables, your phone executes complex tasks instantly and silently. The massive leap in processing capability came directly from engineering the microscopic voids between atoms. During the space race, computational power was a scarce and highly rationed resource. Today, you carry a massive surplus of it everywhere you go. To compensate for their severely limited hardware, the Apollo teams relied heavily on rigorous manual testing, flawless mathematics, and raw human courage. Through that immense human effort, they successfully navigated the vacuum of space and stepped onto the lunar surface. Modern silicon has removed that specific friction entirely. Raw computational capability is no longer the bottleneck holding back human achievement. You go about your daily routine carrying the functional equivalent of 1 million moon landing supercomputers resting quietly in your palm. With the limits of computing power virtually erased, the only question left is what endeavor we will choose to target next.